Hey everyone. Okay, back for Kepler's second law of motion. Okay, so Kepler's second law of planetary motion, we're going to understand and apply Kepler's second law of planetary motion. All right, Mars is a weirdo, okay? So Kepler studied Mars in the 1600s because it did not fit with any of the proposed models of how planets move at the time. Remember, at the time, Ptolemy, Copernicus, and Brahe, who Kepler was studying under, said that planets actually move in this circular orbit. And Kepler's like, no, first law of planetary motion, they actually travel in an elliptical orbit. So his second law is known as equal area and equal time, okay, or equal area and equal time law. So the area swept out in a fixed amount of time is the same while the planet is orbiting the sun. So what that works out to mean is that as a planet is farther from the sun towards its aphelion, it's actually traveling slower when it's farther away or farthest away, and then it speeds up. Its velocity changes and speeds up as it gets closer to the perihelion, which would be coming closer to the sun. So this area 1 here is the same as this area 2, even though it's farther away. That like triangle is stretched out, so they end up being the same equal area. Okay. So Mars did not move at the same velocity throughout its path. That's why it's such a weirdo. Planets do not move at the same velocity throughout its whole orbit, but Mars was more exaggerated because it's very close to the sun. Generalized to all planets, the sun-planet line sweeps out equal area and equal time. Okay, something that's important to understand when we're thinking about Kepler's second law, something that was not well known at the time, is conservation of angular momentum. So this is a concept that wasn't known in Kepler's time, but it helps explain this movement of planets and the change in their velocity as they orbit the sun. This is a measure of rotational motion. It is like a figure skater, okay? So if you've ever seen a figure skater, if you haven't, go watch a video real quick of it, come back. But a figure skater, if they have their arms out, they have a wider radius, they are moving at a slower pace. And then when they do their turns, right, they have their arms out and then they bring their arms in, what happens? Well, they've decreased that radius, and so what happens because of conservation of rotational or angular momentum is that they start to speed up. So they travel faster, right? They spin faster and faster and faster. This is known as angular momentum. And this also means that the angular momentum is kept constant between the sun and the planet. That is why that velocity is changing. As it gets farther away, it slows down. As it gets closer, it speeds up. Okay, so here's my little figure skater, right? So if they have their arms out, they're traveling slower, they pull their arms in, they suddenly speed up. Okay, so same idea here. Okay, quick summary. Kepler determined that a planet's orbit will sweep equal area and equal time. Due to conservation of angular momentum, a planet's velocity is not constant, but speeds up when it is closer to a focus and slows down as it is farther from a focus. We need to keep in mind this directly applies with how close or far away it is from the sun. All right, so catch me on the next video, Kepler's third law.